All right, hello everyone. Welcome to episode 21 of Warsaw.AI Meetups. My name is Pavel. I will be the moderator today. We'll have opportunity to listen to three great talks. So Mikołaj Koszowski from Allegro will tell us about machine translation at Allegro. Use your model wise, but data wiser. Then Andrzej Mizera from Ideas and CPR will tell about deep reinforcement learning based approach towards effective cellular reprogramming. And finally, Michal Marcinkiewicz from NVIDIA will tell about LLM in MLPerf, accelerating large language models training at scale. And finally, after the talks, there will be the after party. So, of course, we also invite you to stay with us and stay for the networking. But before we start, there will be the announcement of the winner of the Jetson Nano giveaway competition. So I believe that at least some of you heard about it. In the registration form, there was an option to tell us what would you do if you won the NVIDIA Jetson Nano. So we promised to give it today during the event. So the winner is Krzysztof Jankowski. Is Krzysztof with us? Yes, Krzysztof is with us. So big applause for Krzysztof. Congratulations. So the answer, the comment, maybe you can read it and tell us what will you do with this Jetson Nano?
Okay. So I am a big fan of reinforcement learning. So with Jetson Nano, I would start to move my efficient reinforcement learning agents from a simulated environment into a fully autonomous robotic agent, exploring and learning in a real world on its own. And by combining new efficient algorithms in computer vision and reinforcement learning, I would start paving the way for RL agents in robotics that could in the future start helping humans in our daily tasks.
Great. So we keep the fingers crossed for this goal, and so here's your Jetson Nano. Congratulations once again. And maybe just one comment, because we received more than 20 submissions, 20 comments. Okay, we can. All right, will be a photo taken. So yeah, maybe, okay. There were more than 20 submissions, more than 20 comments, and many of them are really great, so it was difficult for us to make the decision. But as at least some of you remember, Krzysztof was a speaker during our last Warsaw.AI meetup. So we already had the opportunity to see and to learn what he can do in machine learning, that we were certain that he can do really good stuff. This was also one of the reasons why we selected Krzysztof as the winner this time. Maybe there will be some similar competitions in the future, so stay tuned, of course. Congratulations once again. So thanks, Krzysztof. Thank you. Okay, and before we proceed, I would also like to thank our sponsors, partners, organizers. So this event is co-organized by the Quantum AI Foundation and Ideas and CBR, but we also thank Allegro for hosting us. It's our pleasure to be here in the next year, in fact, because we started in 2022, so it's already 7th meetup, probably 7th. Yes, and we hope to continue our collaboration in the future. And a few months ago, we started releasing our weekly newsletter, Warsaw.AI News. So we also invite you to subscribe if you haven't done it yet. And of course, we invite you to join and follow our Facebook, LinkedIn, Twitter profiles. All right, so I think we can start and go to the first presentation, right? So Mikołaj Koszowski will tell about machine translation at Allegro.
So hi you all, do you hear me well? And yeah, so I will talk about our machine translation at Allegro. It's important because we are going international. So Allegro is now available in Czechia and soon will be in Slovakia and other countries of Central and Eastern Europe. Okay, agenda for this talk is business stuff, like business case for this machine translation done internally. Second is how we build machine translation. I will talk about our training pipeline. Then we'll talk about what does it mean to be production ready. And finally, closing with happy ending. Spoiler alert, we get the Czechia launch with our internal machine translation model. So yeah, buyers want it convenient. And what does it mean? They want the marketplace in their own language, in native language. So we need to translate whole Allegro to other languages. For now, it's Czechia. It's also available in English. And we have some part translated to Ukrainian when the war happened. And what does it mean to translate Allegro? It means a lot of translation is needed, but there are many different content types. So for example, we have interface, which is quite small. There are not a lot of content for interface. It's like category names, parameter names, and so on. Also, there are like help articles that needs to be translated, and we have a different amount of data that needs to be translated. So for example, communication is around 100,000 messages, and products is even order of magnitude bigger with 100 million products available on Allegro. So we have options to consider. We can hire professional translators, like human translators. They will give the best possible quality, but it's really costly and slow. So we can also outsource it to the sellers, but sellers probably would use machine translation available online. So it's not really good option because we want the least friction, the biggest amount of sellers available on Allegro from day one. So we won't do that because we also want the control on the final quality. So if we are doing it internally, it would allow us to have better control. So we decided to use machine translation. It's quick and affordable, but the quality is the question mark. There are a lot of like fun examples when the translation goes wrong, especially with different products. Yeah, we decided to use machine translation to once again iterate the scale of this content we need to translate. Even if we hire an whole army of translators, 1,000 of them, it would still took 18 years to translate the product content on Allegro. Yeah, so what is translated? We have product names, offer titles, and descriptions. That's so-called dynamic content because it's generated by the sellers. So this is the conundrum. Do you use something off the shelf or develop internal capabilities to translate? I think many of you have these questions, and the answer is really hard. Like, it's quite risky because we didn't do something similar before, but have a lot of advantages from our point of view. So I'm coming from the team called Machine Learning Research, and we have the confidence that we can train machine translation model. But can we build the needed solution for the company? That's the question. So we started with research project. In our work, we have like 20% of work time that we can allocate for research purposes. So we allocated it for training machine translation models, and it have like good outcome because we trained the models, we published the paper on the conference in 2021. So yeah, we have this first step, like convince other people to allow us to build this product. So now we're moving to proof of concept phase. And here we need to answer a lot of questions. And also convince others that this is not risky. We can deliver the needed results. So what are the advantages we use to convince others? it was that our translation would be tailored to e-commerce. We can do some domain adaptation. Also, it would be really, really cost efficient. I will talk about it why later. So it would be orders of magnitude cheaper. Also, we can improve it iteratively, including human feedback from our sellers or buyers. And finally, we get new competencies in our teams that proven really useful during the Czechia hard launch. Yeah, this is some of the questions we needed to answer before we get the green light on developing the product. Like, what are the challenges of translating e-commerce? If they are similar to the research test set or so on. So there are a lot of questions, but we finally given the answer, we get the green light. So how to build something this big? The answer is brick by brick, slowly, from the bottom up. So Allegro Machine Translation Service, to build it, we need strong foundation. And our foundation is data. Data is 90% of success. We have this data-centric approach. We have like now LLMs that data is the secret sauce. So data is the bedrock of our solution. But we also need so-called business rules. They shield us from making some critical from the point of view of e-commerce mistakes. I will talk about it later. And we also need to decide on good architecture that could be deployed easily and like have trade-off between quality and speed. And finally, we need human evaluation because I will tell you about it later, but it helped us a lot to develop robust and good translations. Machine translation services have other aspects as well, but yeah, I won't have time to talk about it today. So let's focus on building strong foundation so our Tower of Babel won't collapse, hopefully. So how to train machine translation model? Similar to humans, you need to have a sentence in 2 languages. This pair of sentences is our training example. So I will call it parallel data because of this aspect that we have the pair. Also, I would call it corpora sometimes because it's like lingo used in machine translation. Corpora just means collection of text. And we have different kinds of data available, this parallel data. We have general language. We have around over 100 million pairs of sentences. We also have 1 million sentences that are e-commerce. But unfortunately, we don't have any parallel data for Allegro because it was only Polish marketplace at that time. Yeah, diving deeper into the data, general language is like publicly available open sources datasets. It's mostly thanks to European Union initiatives like grants and so on. There are a lot of open source data. We can also use plain text in other languages, but it didn't give any significant improvements, so let's skip it for now. The e-commerce lingo is coming from Mall Group. So Allegro went international partly by buying Mall Group. So we have this Czech marketplace that also sells some products to Poland, and we extracted the same sentences from the Mall PL products. And what is also important that we have this really big assortment of Mall products that are Czech only, so in Czech language. We will make use of that because more data, more high quality data, the better. And finally, we have massive amounts, as you've seen, like hundreds of millions of products from Allegro.pl. So we make use of that data also. So few words about architecture and system design. We are using vanilla transformer from well-known paper, Attention is All You Need. It's transformer big. It has 200 million parameters, but it's not so big for current standards. Like currently 7 billion parameters is called small. So we are like really small model that we can train efficiently because we are using cloud GPUs for training. We can train the model from random initialization to the final model in like 1 or 2 days. It gives us the ability to iterate quickly, but we want the model to be able to be served on CPUs. And more about it, I think now, because we have 2 data centers in Allegro, our own data centers. And we operate only in 1 time zone. So in the night, these CPUs are waiting for something to do. And we found them the task to do, they are translating. And it's like basically free compute. Yeah, and another design decision is about teacher-student. This approach is called knowledge distillation. We are using, let's assume we have the models ready. We are using 4 models to distill the knowledge into one. So this distilled model behaves as good as the 4 models simultaneously. Also, this is the advantages of like day-to-day work, the operational work. So we have these teachers, and they're more research-oriented, and we have this student, this blue one, which is like more production-ready, more final model. So it's easier to track and develop the model. And also why we choose to do this knowledge distillation, because it's the step where we can include the Polish Allegro, this massive amounts of data. Also, advantages of using knowledge distillation is that the student model is much easier to quantize. So we can like use lower precision during compute, and it's like 4 times smaller and 30% more efficient. So diving back into the data. How to use this e-commerce check data and how to use this Allegro data. So we're using so-called back translation. First, you take the general data and this small parallel data I mentioned at the beginning, and train the model that could translate from Czech to Polish. Then you take the Czech-only e-commerce data and use this additional auxiliary model to create translation. And you now have parallel data from Czech to Polish. I would indicate the synthetic parallel data because it's partially synthetic, but the Czech side is original data, high quality data. And then you combine the general parallel data with this newly created e-commerce parallel data and train teacher models. I think many of you consider why this works. Like, why this back translation? You are like bootstrapping. It works because translation have 2 aspects: accuracy of translation and also the fluency of translation. The neural models, the transformer was big change because it became really fluent. You can generate fluent text. And this back translation helps with this fluency aspect because of this original Czech data you have in your dataset. This is also the step where we are experimenting with different data filtering, different approaches for like optimizer or learning curve, and so on and so on. But then next step, if we have really good 4 teacher models, we are taking Polish side of all of the data, and now also the Allegro, massive amounts of Allegro data. We are translating it using this ensemble and choosing the best translation. So for example, for parallel data we can like choose the most similar translation to the original outcome. And for Allegro, we choose the highest probability translation. And now we can train student model, and it's it, finito. It's ready for deployment. Not so fast. Like we need to confirm the quality of translation with the human evaluation. We've decided to use acceptable translation rate. It's our KPI internally, but it's connected to the scale. We are using the scale from 1 to 7. We're having 5 annotators to annotate each translation. But the trickiest part was not deciding on the scale, but what each of the steps in the scale means. We wrote like really detailed guideline, and thanks to using professional translators for the annotation, we have really high agreement between our annotators. And we are quite confident in our results. So our Allegro translation engine, our machine translation engine, have the acceptable translation rate of around 85 to 90%, depending on the translated content type. And what's really cool is that after the launch of Czechia Marketplace, we used some UX tests and asked our buyers if this translation is acceptable or not. And it correlated really well. Around 80 or 90% of buyers are content with, are happy with our translations. And why human evaluation is important and something to consider, because this is really funny description we found thanks to human evaluation. After we included images in our text evaluation, so different modality, the annotators came back with these comments that it's really weird. Why are you showing this to us? Like for English speakers, it's like salt grinder, and the description is really poetic. You have like salvation of the soul, the frog, the pepper frog, and so on. Like it's total gibberish. It's important like to remember that garbage in, garbage out. You need to have that in mind. But one thing that was not so funny, and thanks to human evaluation we catch, we are using probabilistic models. So probabilistic models makes mistakes, but some mistakes are crucial. And in the e-commerce domain, I will give you a few seconds to think about why this, how we could translate this sentence badly, that it would have really critical e-commerce error. So the sentence is about the most comfortable mattress, 200 by 200 of well-known brand with emoji at the end. And this is just a use case. Our model didn't make that mistake, but yeah, the mistakes is about dimensions of the product. It's really critical. We shouldn't make that mistakes. We also translated the brand name. That's also critical. Some minor mistakes happen also in the presentation. The emoji disappeared, but it was swapped in the example, and so this presentation like tricked me. But also the boundaries was like placed in the wrong place. So we found these common edge cases and how to address them. Like we have this probabilistic model that would make mistakes. How to make a deterministic model? We found a solution, and the solution is to include special tokens, special tags. So before translating, we are preprocessing the data. Our translation model understands the special tokens and translate, producing the same tokens. And then we just simply like replacing the tokens. And now we have like properly translated text. The numbers are preserved, the brand name is preserved, and emoji also. So now we can sleep well. And yeah, that was the happy ending for today. Buyers are happy because they can shop in their own native language. Sellers are happy because they can sell without the friction, without the need to provide translation. And we are happy as Allegro translation engine team because we built something big. We built something with the important impact on how quickly we can make our company international. So yeah, it was one of the enablers for quick internationalization. Yep, that's it. Thank you for attention.
Okay, we have a few minutes for questions. Do we have any questions? Maybe okay, there's one.
Can you move to the before the last? Oh yeah, here. You are pre-processing. It's
Yep.
how do you do it with like you're getting every title and you are going like tagging in manually, or you are creating some model for it, or
Yeah, so it's like mixture of things. We replacing the HTML tags. It's like simple string matching. Also for number, we have like numbers. We have like regexes, regex stuff basically. But for the brand names, it's quite tricky. But Allegro has these parameters, and for the product, often the parameter is the brand name. So we can string match for brand names from parameters for given product.
thank you.
All right, one more question.
Yeah, hi, thank you for presentation. As far as I see, you started to train model from scratch.
Yep.
Have you tried to use some open source models to fine tune them, and what was as a result in comparison to the current pipeline?
Yeah, so we started with that. It was done for our proof of concept phase. We started with some pre-trained open source models. But fortunately, we found out that it's better to train from scratch. Fortunately, because this pre-trained models, it's not clear that you can use it commercially sometimes. So we mitigated those licenses issues. So yeah, it was a good outcome because training from scratch, from random initialization works a bit better, but you train for longer. But we train for 1 or 2 days, so it's not a problem.
All right, thank you. Last question.
How did you decide on the number of parameters of the model?
Yeah, we like make experiments with increasing the model size and found out that the gains are not really. We have, of course, automatic testing and test sets, and found out the gains wasn't big enough to just use it. So the transformer big architecture proposed in the paper is like really good trade-off between the speed and the quality. And using this teacher-student approach, this knowledge distillation, we can like have different sizes for the students and the teachers. So we can like go for even bigger models. We are planning for something like that, like go big for teachers and still use the transformer big for the student. So yeah, we didn't see significant gains.
All right, we have to move to the next presentation, but Mikołaj will stay with us for the after party. Yes?
Sure.
So if you have more questions, you can ask then. Thank you. Thanks, Mikołaj. Thank you once again.
Thank you.
All right, and now it's time for our second speaker. So Andrzej Mizera from Ideas on CVR.
Okay, so thank you very much for the introduction. And first of all, I would like to thank the organizers for giving me the opportunity to be here with you today and share my research with you. So this is quite or rather interdisciplinary research that we are conducting here. And my presentation is basically split into two parts. First, I will give biological context for our research. So I need to do some introduction, biological introduction. This will be the first part of the talk. And then I will move to the computational part and how do we solve the problem with classical approaches, and then how do we go further and use machine learning for solving biological problems. So the biological background and motivation for our study, as basically we all know, we're complex. I mean, humans, organisms, are complex entities. Roughly speaking, there are 200 different cell types that constitute a grown human body. And all these cells, they originate from a single embryon, right? From a single cell, basically our whole body is built. And this is happening due to the process of cellular differentiation, in which a stem cell changes from one type to, it proliferates and it changes from one type to some specialized, differentiated other type, and so on. So with this process, there is an associated notion of cell potency, and this is the ability of a cell to differentiate into other cell types. And for example, if we talk about the embryonic stem cells, they are pluripotent. Basically, this means they have the potential to differentiate into any of the three germ layers, endoderm, mesoderm, or ectoderm. And with time, when these cells that differentiate, they kind of lose their potential or this cell potency. So for example, stem cells derived from some adult tissues, they are called to be multipotent, which means they have some limited tissue-specific regeneration potential, right? So for example, the skin stem cells, they basically can regenerate our skin. If we are we make a cut, we can, our cells, these stem cells in the skin can regenerate the skin, but of course they cannot generate other organs. So this cell potency is slowly lost as the cell differentiates and gains specialized functions. So for example, in somatic cells. And the concept of development, it was first somehow explained, let's say, by Conrad Hall-Waddington, a British developmental biologist in 1957. He proposed the concept of an epigenetic landscape. So this is nowadays a famous visual metaphor for the embryonic development and cellular commitment. It basically, this concept of the landscape, it unites the embryology, so the embryological development, and genetics. And the idea, originally what Conrad Waddington proposed was that the development is viewed as a ball which is rolling down the landscape, and finally as it moves, it arrives at different valleys in this landscape, and these valleys are associated with different cell types. And of course, the barriers, these hills, there are barriers which basically isolate these valleys. And in this landscape, we have different kinds of valleys, and they really kind of correspond to different cell types that can be generated. But the idea, when this picture was presented, it somehow changed the way of thinking about different development. And what came to the researcher's mind was that basically differentiation is not terminal, and that these epigenetic barriers then can be overcome. And we can basically change cell type or enforce the cells to change type. So then, of course, initially this was just like a visual metaphor, and there was just an concept which help to understand how the development is happening and how the process is running. But then with the 20th century knowledge, when we started to understand what the genes are, what the gene regulatory networks are, it turned out that this becomes more and more concrete, this concept, and actually that this landscape can be thought of as being shaped by the gene regulatory network. So the idea is that we have the expression of genes, which is a fundamental process in living cells. It is central to the control of intracellular processes and the response of a cell to environmental signals. And what is crucial is to be able to regulate the gene expression. And for this, we have the interconnected network of genes which interact with each other, and we refer to this network as the gene regulatory network. So it basically consists of genes, proteins, mRNAs, so products of the genes, and they form these intricate, sophisticated networks that basically allow us allow the cell to function and to respond to the signals which come from the environment and to adjust to these conditions. And of course, in the case of a multicellular organism, as for example a human being, we know that there is only one gene regulatory network which is common to all the cells in the organism, but we have different cell types. So somehow this gene regulatory network allows these different cell types to be present. And this is basically the cell types. They are associated with distinct stable gene expression profiles of the gene of the genome in our body. Okay. So then we are coming to the problem of cellular reprogramming. So what we actually want to do, we want to be able to move around the epigenetic landscape. We want to be able to move the cells from one place to another. So for example, we have one cell which is in one valley, which is a one cell type, and we would like to either put it up and maybe then redirect it to the target valley, target cell type. So this is called basically reprogramming. We are putting this cell up the landscape, and we are then guiding the cell to the more pluripotent state, and then driving it toward the differentiated target cell type. Or we can think of direct reprogramming, where we change directly one cell type into another. Okay, and of course this has, at least theoretically, this has a great potential. It could be applied to disease modeling, drug design, organ synthesis, and so on. So what is the problem here is that in wet lab, I mean, how to do it? Okay, so we basically need to somehow manipulate the genes in the one cell type in order to transform it into another cell type. And to identify what to manipulate is a challenging problem. So if we want to do it in the lab, it is very costly, it is very time inefficient. You need to have all these kind of experimental techniques which are not very maybe efficient. So there are a lot of problems how to find strategies to reprogram one cell into another. And one could think, okay, this is maybe some artificial problem. This is not really, okay, we can imagine this, but is it really happening? Can we really do it? And it turns out that we have a few successful, inspiring stories. So all this started basically in 2006 when Shinya Yamanaka was able to generate induced pluripotent stem cells from adult mouse fibroblasts just with 4 transcription factors. So among these thousands of genes, he selected, basically turned off 4 of them and was able to change the cell type. Next, of course, for this in 2012, he got the Nobel Prize. And then in 2017, there was a case of a boy who was suffering from a severe disease. Basically, he was losing 80% of his skin. He couldn't function. He was in coma. And then there was the team of Professor Michel De Luca, which kind of with the use of cellular reprogramming, there were also other techniques, of course, used there, but one of them was cellular reprogramming. He managed to basically produce the skin for the boy, like it was about 1 square meter of skin, basically do the transplantation, and now the boy is living, he's running, playing football, having a normal life. And then last year, the team of Professor Jakob Hanna from the Weizmann Institute grows the first complete human day 14 embryo model without sperm and egg. So basically, if you look into the data, I think they were using some skin cells, and they were able to reprogram them into stem cells. And then from these stem cells, they produced 4 types of specific cell types. And then when they put them into a mixture, suddenly 1% of them generated something which was basically exactly a human embryo. Okay, so these are the successful stories, and let's slowly move on to the now computational part. So basically what we see is that these cell types may be related to balanced states of an underlying regulatory system. This bears striking resemblance to modern mathematical notion of attractors in a dynamical system. And in our case, we considered a very simple framework of Boolean networks. So we want to model the whole or large part of the genome with Boolean networks. So the advantage is these Boolean networks were introduced by Stuart Kauffman in 1969. This is quite a famous framework, and it has the advantages. Mainly, it is simple. So it is consisting only of variables, and which represent the gene being on and off. And these genes are regulated by Boolean functions. So this framework has very clear structure, but at the same time, it has very rich dynamics. So the dynamics is nonlinear, it is rich, and can model many phenomena. So what we have in this framework, we have the Boolean functions. Based on the Boolean functions, we can see what are the dependencies between the genes. So we get this graph of the network structure. And then the problem is that once we have the network structure, we have the Boolean functions, and then we want to see how this model will evolve in time. And for this, we need to assume some update mode. Usually, for biological processes, we use the asynchronous mode. So this is the one which is more realistic. And this gives rise to the non-deterministic graph of transitions between states, which is called the state transition graph. The problem is that the size of the graph is exponential in the size of the network. Now, if you think of a human genome, we have 30,000, roughly speaking, 30,000 of genes. So the size of such a simple, of the dynamics of the state transition graph of a Boolean network, which would model the whole genome, would be 2 to the power 30,000, which is a crazy number. And so still, we of course cannot model everything, but we would like to model as much as possible because we are dealing with complex systems and they have emergent properties. So we need to consider as much as possible put together. We cannot really decompose the network. And it turns out that these states, they're called attractors, so the trap states in this state transition graph, they correspond to the various cell phenotypes. And this was also shown in the literature. You can see here that these attractors, they were really corresponding to some biological processes. So now we have the new picture of the development. We have the genome, we have the gene regulatory network. This gives, when we have the structure, we have the dynamics, we have the gene expression pattern, which are the network states. And of course, these numbers are exponential in the number of genes. We can map it to the states, two-dimensional state space. And then if we consider some kind of a potential, we basically get back to the picture of but now a mathematical formulation of the epigenetic landscape of Waddington. And what is happening here is, of course, that, okay, we have multiple valleys, but there are also some valleys that are not visited normally. And this is postulated that basically these are the cancer attractors, and this is the price the complex organisms pay for the multicellular development. So these somehow, some cancer attractors or unhealthy attractors are immanent to the functioning of the multicellular organism. So now the problem is, now we're getting to the solution of our problem. We want to find this how do we manipulate now the mathematical model, which is the Boolean network, in such a way that we can drive the system from one attractor to another attractor. And for this, it is already known that it is usually not enough, and this is also the biological reality. One drug is not enough. We need to consider combinations. So we are dealing with a difficult problem here. We need to consider multiple biological targets, and we need to search them in such a way that at the same time this is an efficient process, so we can efficiently go from one attractor to another, and that that these numbers are not too big, because otherwise it would be complicated to do in the lab. So we have, in my research previous years, I was considering this kind of classical approach to this problem, where you have your network, you have your model, then you have the state transition graph. Of course, you cannot really construct it explicitly in the memory for large network. It's just too big. But basically, the idea is that if you want to go from one attractor to another, you basically need to consider something which is called a strong basin. So states which directly will deterministically will lead these dynamics to the target attractor. You need to somehow compute this set, and then you can identify how do you change, what is the minimum, let's say, modification you need to do in this state to get to the strong basin, so that the dynamics then drives you to the target attractor. And of course, this is like, let's say, basically a formulation of what I just said. And what we were working on was to find ways to actually do it. So we have, let's say, large networks, because we need to consider large networks if we want to be realistic and have some correspondence with biological processes. So the classical algorithmic approach, of course, was to do some kind of divide and conquer approach. So we were developing algorithms where you basically could decompose the structure of the graph into parts. You were considering the parts somehow individually, computing partial attractors, computing partial strategies, and then we were showing that, okay, you can basically merge these results so that you finally restore the attractors, then the control strategies for the whole network. Now, the problem is that, in general, already the problem of finding the attractors is NP complete if you consider one state attractors. If you want to go further, it becomes even NP hard. And finding the strategies is even harder problem. So we can do it because we use the fact that in biology, usually the networks, they have some hierarchy, they have some modules. So you can basically somehow decompose them, and with this kind of clever approach, you can compute these strategies and attractors and the strategies. But the problem is that sometimes it can happen that still this module is too big, and then you cannot do anything. You cannot decompose, then it doesn't fit in memory, you cannot construct the graphs. Of course, we are using some symbolic operation like binary decision diagrams to solve this problem, but still, at some point you get stuck. So now how to get scalability for this issue? And the idea is, okay, let's do something similar to what was done to play Go, because we have huge state space here. We have many states, right? I mean, we have this exponential state space explosion. And we have multiple actions that in principle you could take in each step to state to drive the system to the target attractor, the one that we want, let's say from the unhealthy attractor to the healthy attractor. So for this, we consider now, this is something that we are just finalizing our first paper on this, where we consider deep learning to see if we can really mimic this approach, use this DRL to drive the system from the source to the target attractor. And there are still problems here, because of course this is the slide that I have for kind of showing how this DRL works here. So we consider this model as our environment for the learning. And there are two approaches here. One is, okay, you have the network. The network is maybe large, but somehow you know the attractors. So this is one thing, you know the attractors. And then, of course, our actions that we want to do, they should not be in arbitrary states, because we want to be somehow realistic here. We want to be able to, once we get the strategy from the model, we want to be able to take it to the lab. So we need to apply these strategies whenever we are in a state that we can kind of recognize. So this means that we can basically do it, only apply actions which we are in attractors. So we can consider intermediate attractors on the way from the source to the target. And we can apply the actions only when we are in attractor states. So that could be intermediate attractors. So we have a path which goes from one attractor to another over other attractors. And the actions can be only applied in the attractors. But the second thing which is challenging here is that, okay, if I have a big network, I usually don't know the attractors. So I am combining the fact that I am looking for the strategy with, so I'm playing, let's say, with my environment. The game is that, okay, I do some actions and I see if this action is taking me to the target attractor. If not, the episode ends. I get the reward, which is negative, some penalty for not reaching the attractor, and so on. So this is kind of standard. But the problem in our case is that usually we don't know the attractors. So we don't know where we can apply these actions. And during the training, we are somehow monitoring the training and dynamically updating the list of attractors. So we're detecting attractors at the same time. But this destroys the training. So there is because then the network has learned something and suddenly it has a new possibility to apply action. So it has dynamically to adjust to this new situation. And the play here, the problem here, and this is what basically part of our paper that we want to finalize next week, basically, is that we show that there are some rewards that actually help with this problem. So that we have some strategies that actually, if the reward is of certain type, it allows us to control the situation and improve the learning. So even we detect new attractors, we can quickly, the cost function is increasing, but then we are able to reduce it quickly, and somehow this model adapts quickly to the situation that it discovered new possibilities for taking this action. So the idea is the process of detecting attractors during the training for the strategies, and then how should we construct the reward function, and then of course what is the right architecture for these kind of problems. Okay. And where do we want to go with this? Well, basically, this is kind of funny picture, but we want to basically be able to shape this landscape in accordance with our needs. We want to be able to tweak it in such a way that we are able to take the cells to the valley of our desire, right? So from, let's say, unhealthy cell to the healthy cell. Okay, and with this, I would like to conclude my talk. Thank you.
All right. Do we have any questions to Andrzej? Yes.
So basically, if I understand, thanks for the like great presentation. So basically, if I understand, so you can you go back to a slide of this network? Yeah, for example, this. Yeah.
This
so
one, yep.
Yeah. So we have a state 110, and then 110 can go to, from one state we can go to either 100 or 010, right? This is the thing.
Yeah. So we need to consider this strong basing. So basically, the only state here which is certain to take us here is this one, right?
Okay, maybe in simple word, I'm trying to understand. So we have a state 110,
yeah,
right? And from one state we have two possibilities, right?
Yes.
Okay.
You mean this?
Three possibilities.
Three. One,
Yeah, okay.
2, and 3. Yes.
And so now we have 33,000 genes.
So the number of genes here is 3, and you can imagine. Okay, let's take a network, reasonable, let's say network for some purposes. Let's say 200 genes.
Yeah, okay.
Which means that you have 200 ones and zeros, and the number of states is 2 to the power 200.
Yeah. So, but so we have a whatever number of genes, and we have a starting state.
Yes.
And we are interested when this all, like, we can have a different combination and they reach to a different attractor, right?
Yeah.
So I still see it's not that complex problem. I mean,
so what,
because if we know if you know evolutions of the state, or we can kind of like find, like, you know, go through different evolutions of the state, maybe like this experimental problem, I guess. So this is.
So the problem is, of course, this problem can be very easy, made very easy. If I can manipulate all 3 genes, I can directly tweak them to go directly here to here. The problem is that usually in the lab, I can play maybe with 3, 4, maybe 6 genes, right? And I don't know which ones. And I want to do it efficiently. So I want to do it in such a way that because these experiments are costly, they take time, they are not reliable. So I want to repeat this as I don't want to take many steps, and I don't want to intervene with many genes at the same time. So optimally, I would say, okay, I do it like in the Yamanaka case. I modify, or I put 4 transcription factors, which means that I manipulate 4 genes, which turn them on and off as wished. And this is enough. Once they are introduced, they change the expression pattern of these 4 genes, and then I let it go. And the dynamics takes me naturally to the target attract. And the problem is how to find the optimal strategy. So that's the shortest one, which as quickly as possible takes me to the target attract.
And why you call it non-deterministic evolution?
Because I have what we are modeling is the asynchronous update mode. So asynchronous means that when we do the update, we select randomly one gene and we update it in accordance with its Boolean function. But the problem is that you update, you don't know which one you will select. So in principle, from one state, you have as many outgoing arrows as the number of genes. Of course, some of them can give you the same result, but in general, you have like 3 genes, so you can randomly choose one and update one. Another update mode is the synchronous update mode, where you update all the genes at once. So you are in a state, you compute the Boolean functions for each gene, they give you the target state. Then the dynamics is deterministic because you have only one possible transition.
Okay, thank you.
All right. Any more questions?
Hello, thank you for the great presentation. I don't want you to spoil the paper, but can you tell us a little about the types of models for reinforcement learning models that you considered during the...
So we based this on a previous study. So there was dueling double Q networks which were used. But for the problem there was different because in that paper the update was synchronous, so the problem was slightly different, and they were allowing only one gene to be intervened with at a time. So when you do the action, you could only play with one gene. But we were able to show that basically there are cases or examples of networks where with this kind of manipulation, you are not able to go from one attractor to the other. So we had to extend this, and of course, this is also the reality, as I said. I mean, in reality, the biological networks, they are robust. So simple diseases you can heal with a single drug, basically. But the more complex the disease, the combination of drugs you need to use to basically heal the patient. And this strategy mimics this situation, so we allow up to a specified number of genes to be intervened at a time. So this is an action. And for this, we had to change the network. So we are using branching double Q networks. So basically, where you have like basically outputs are for as many intervention genes as you want to intervene with, and they are suggesting which gene to intervene, and then you put them together. Okay, so this is something we did, but we kind of modified the architecture, but the main problem was also to play with the reward. So there was like a strategy. This would require a little bit more details. What was the problem? But in general, because you learn new attractors during or pseudo attractors as we call them, you learn them during the training. The problem is that you kind of disturb what you have already learned. And then you have to adjust this reward function so that it kind of allows you to keep it under control, let's say.
All right, we have to go to the next presentation. So thank you, Andrzej, for answering all the questions. And great presentation, thanks. And now it's time for our third speaker, Michal Marcinkiewicz from NVIDIA.
Hello, everyone. My name is Michal Marcinkiewicz. I'm a senior deep learning engineer at NVIDIA. And today we'll be talking about LLM in MLPerf. We have a quite large team at Warsaw that we are working on accelerating benchmarks of MLPerf and making sure we have successful submissions. And today I would like to share some details about the last submission, what we did, and maybe share some interesting optimizations we applied. Some are funky, some are kind of interesting, so I hope we'll get something out of it. Now, a couple of words about MLPerf. Some time ago, a couple of years ago, some corporations involved in accelerated software and hardware got together and figured out that, you know, what would be great, that we agreed on a standardized benchmark that we can, you know, compare each other's solutions and make sure that the customers are well informed about which software or hardware to buy. That's how ML Commons and MLPerf were born. And currently, we have 9 benchmarks that kind of try to represent the whole landscape of deep learning in the world. We hope we did a good job by doing that. Sadly or not, nowadays only LLMs and SD matter. There is a bunch of legacy benchmarks that are, well, were very popular back then, but now LLM and SD are the most important ones, hence I'm talking about LLMs. Some details about MLPerf. We have 2 submissions per year, which are kind of our releases. And there's a single metric that describes whether determines the score of the submission, which is time to train. Also, some more details. There are 3 categories. Available, prevent, R&D. Available means, of course, that you can actually go outside and buy the stuff. Preview is the stuff is going to be available soon. And R&D is whatever you have in your lab, you can show off if you want. There is also HPC category, but we don't talk about it because, well, nobody cares. Let's go then. Okay, now more details about LLMs. So model is GPT-3 175B. Dataset is C4. And now this is kind of critical. When I talk about training LLM, I don't talk about training it end-to-end. It trains for a very long time, and that's not a very good benchmark. So we decided to cut it short. So the entry level is not that hard. So smaller companies can also take part. So we are starting from a checkpoint, and we are training for around 1.2 billion tokens to achieve a particular accuracy. When we reach that, we stop the training, we stop the timer, and that's our score. On the submission, we have 3 runs. We discard the fastest one, the slowest one, and the middle one is our final score. Okay, and this is the results that we obtained in October in 3.1 edition. And let me actually walk you through that. So let's maybe first look at the image. So on the y-axis, we have time to train, which is the MLPerf score. On the x-axis, we have number of GPUs. There is a log scale there. So you can kind of see the scaling efficiency. So we started from relatively small scale, which is 512 GPUs. That trained a little below 1 hour. And also in the small scale category, we considered 7068 GPUs, which is around 40 minutes. And the largest case, we went a bit crazy in October. We ran on 2 large clusters. One was with collaboration with Azure, and one was our internal that we ran on 10,752 GPUs. The time to train, again, this is not end-to-end. This is just the benchmark, is around 4 minutes on both systems, which was actually a coincidence that the number of nodes was the same, but we are super happy we were able to achieve that. Now, if you want to look at the perspective, so the original GPT was trained using 300 billion tokens, but according to the Chinchilla Compute Optimal, it should have been trained with 3.7 tera tokens, which would take 8 days on 10K GPUs, or the original GPT would be trained in like 16 hours end-to-end, instead of, I don't know how many weeks they took on V100s. Now, talking about scaling efficiency, LLM is a crazy scalable model. When we scale it up by doubling the number of nodes, we retain 93% of the performance, which is quite good. We are still working to improve that. Okay, now talking about performance optimizations in general. So it might be worth to divide it to kind of 2 categories. First category is GPU workload optimizations, and the other one, everything else. So for GPU, the rule of thumb is to keep GPU busy. If your GPU is waiting for data, is waiting for anything, you are doing something wrong. But also, if it runs garbage kernels, then it's not really count like as keeping GPU busy. Your kernels have to be fairly optimized. Please don't run loops in your kernels. Then you can use the whole GPU to do efficient work. On the other hand, there are peripherals on the nodes. We have data loading. Back then, when CNNs were the thing, that was really important because loading. Okay, the networks were pretty small, so the I/O should keep up with the data, and that wasn't the case always. However, with LLMs, that's not a problem because the I/O to compute ratio is just crazy towards compute, so that's actually pretty much not a problem right now. However, networking is a problem. You need to have a fast network to keep up with the GPUs, and that's difficult to do. And the last piece is, of course, CPU. CPU and GPU are working in tandem. If your CPU is slow, your GPUs are starved from data, and that's, of course, wasting cycles, wasting money. We try to alleviate the CPU issue by adding CUDA graphs. I don't know if you are using them in your models. They are very stable right now, so I fully recommend. When CUDA graphs don't solve all the issues, we kind of went ahead and designed our own CPU, so now we can run stuff at our pace. And the last piece I wanted to mention is you can kind of rephrase the problem in a different paradigm. So you can use faster math or lower precision in this situation. So standard way back then was running 32-bit precision. However, a couple of years ago, we introduced mixed precision, which was either FP16, then a year or two later, BF16 was introduced. And well, currently the situation is that at NVIDIA, we shout at people for not using mixed precision. Okay, we don't shout at people at NVIDIA, kind of. But this is a standard way to train models. If you don't train it, we will see and we will talk to you and explain to you that that running stuff in FP32 when you don't need it is wasting compute, it's wasting money and starving resources from other teams. So we seriously train everything at NVIDIA with FP16 or lower precision. Now, that was general. Now let's talk about scale. Optimization at scale are a different kind of worms. Let me actually walk you through typical problems at different scales. So I hope I have a pointer, but let's say I'm going from the left to the right. If you run stuff on a single GPU and you have issues, the problem is probably in front of the monitor. You need to fix your code. It sometimes can be a problem with documentation, something is not clear, but that's, let's say, the highest level of issues. If you can get running on single GPU, you want to move to single node. And normally the issues are with the framework. There's something weird, you don't understand something, you need to fix your code. That plus plus kind of means everything before that plus framework. When you go to multi-node, the difficulty kind of rises, let's say, an order of magnitude, and you start to notice the, let's say, hardware, high-level hardware issues. For example, your I/O is not really keeping up because the benchmarks in MLPerf scale strongly, meaning we are having the same problem, we are just throwing more data on that. And in order to kind of converge with more hardware, you need to lower the batch size. And small batch size means small kernels, so you are losing efficiency, and you need to make sure that everything else in the node keeps up, because small kernels for GPU are not really a problem, so GPU runs very, very fast. And also something I call connectivity, meaning if you have a small cluster like 16 nodes, then you need to make sure that everything is connected properly, otherwise you are losing perf, and that's just not very efficient for your training. Now, when you scale up to around, let's say, 1K GPUs, now you start really seeing the issues with networking, meaning your communicators are slow. If you are not using optimal network and your GPUs are starved from data, then you are seeing idle times. And of course, inefficient kernels, meaning if you are going to a very small kernel, even on GPU, you are losing a lot of efficiency. GPUs are not really being used at 100%. Now, the interesting stuff starts happening when you go above 1K nodes, meaning, above 1K GPUs up to, let's say, 10K nodes, 10K GPUs. So first of all, you need to have fast storage on your cluster. What does it mean? If you have a network drive, it's probably not a very good use, meaning if you want to run stuff on 1K nodes, which is 8,000 GPUs, you need to have, for example, your container or your data somewhere. If you want to move your container onto your nodes, that will take ages if you have a slow drive. So really you need to have a parallel file system to keep up with the training data, or don't wait an hour for your job to start. Also, your communication patterns matter a lot. You can lose up to 20–30% of your perf just because you have inefficient communicators. Now, kernels are very small, so CPU overheads are also killing you. You need to make sure that you can avoid that. For example, through CUDA graphs or some other fixes. And again, constant costs. If constant costs I here define as something that you have to pay every time you run stuff, and it doesn't really scale with the number of nodes. And the last part, of course, people bothering you to stop running that because it's kind of, you need to share, right? On 1K nodes, stuff becomes just weird, meaning if you are training on 10K GPUs and single node has a hiccup, I don't know, OS hasn't been updated, everything stops, everything breaks, and you are scratching your head what happened. Also, interesting part, if you are training on a single node or a single GPU, and your code has a race condition, it happens, I don't know, 0.1% cases. So normally what you do, you assume my time is more important than machine time, and you just ignore it, because why not? However, if it happens 0.1% on a single GPU, it happens every time on 10K GPUs, and you need to address that. And also, that's actually a real case. We had a power limit on the data center, and we really couldn't run the whole machine because we would have blown the fuse, and cluster people will really shout at us then. Okay, let's go to optimization. So the first one I'd like to talk about is FP8. I kind of started talking about lower precision with FP16 a couple of minutes ago, but let's talk about FP8. So why do we even bother with FP8? So NVIDIA GPUs have specialized hardware units called tensor cores. And tensor cores are designed to accelerate deep learning kind of math, which will be much faster than standard CUDA cores. Meaning you can parallelize stuff on CUDA cores, but it still is not as efficient as running stuff with tensor cores. Tensor cores can run matrix multiplication 4x4 and addition, for example, bias, in a single operation, which kind of leads to 8 to 64 times faster execution than on standard CUDA cores. It doesn't mean your network runs 64 times faster because you have other overheads and you need to make sure you are using tensor cores efficiently, but it gives a significant speed up. On previous architectures, Volta and Ampere, we supported FP16 tensor cores, but on Ada and Hopper architectures, we are supporting FP8. So this is the real thing that was really designed to accelerate LLM training. Benefits of FP8 are threefold. Two are the most important ones, meaning faster math. You can really get your compute bound operations twice as fast than FP16 tensor cores and more than 4x FP32. Also, if you are memory bound, the ops are twice as fast because half the memory, twice the speed. And also, if you are running inference in lower precision, FP8 or Int8, you have network trained already in FP8, and that should be ready to deploy. Now, how does that work? It's not trivial to run FP8. FP8 is a really small number. Your let's say, way to describe gradients and weights is very limited, so you need to be a bit smart how you do that. So we kind of converge to a situation where we have to use both precisions or formats. So we have, okay, I see this is a type of presentation. So in general, for weights and activations, you need higher precision. Meaning your range can be a bit limited, but you need more bits to describe the precision. On the other hand, gradients don't really care that much. So for gradient, you need higher range, but the precision can be a bit funky because, well, I guess, who cares? There is a lot of tricks to fix gradients like clipping, etc., and network can be trained, so we don't care that much. So what we are using is E4M2 and E4M3 for different purposes, and I will be showing soon how exactly do we do that. Now, of course, you cannot just cast FP16 number to FP8. You need to have a scaling factor, meaning you just need to shift the dynamic range from FP16 to FP8 and make sure that you can shift it back after the computation is completed. So The naive approach is you just scale by the maximum representable value from the absolute maximum of the tensor, and then you have your scale between, well, the lowest negative to the lowest positive value. But that's compute inefficient, meaning what we do in practice is we just take a history and make sure that the tensor are scaled with the history of previous instances of the tensor. Now, how does that work? So as I told you, in the forward pass, when we use activations and weights, we keep everything in E4 and 3 because we need higher precision. We pass that to the layer, and let's say in this case it's a linear layer, and you can get 16-bit activations, meaning you can run your math in FP8, but you should accumulate in FP16. If you don't do that, you just overflow and the network doesn't really train. On the other hand, when you run backward pass, you need a higher range. So you change your format and you get gradient in E5, M2, and the same you can get FP16 gradient backs because you need to accumulate properly. So operations safe in FP8 are, of course, transformer layers. That was designed to do exactly that. But also we are experimenting with convolutions. We get some success. Hopefully soon we will get some out of the door, so you will be able to use it in your ConvNet as well. And surprisingly, Batchstorm also runs properly in FP8. You just need to kind of shift the gradient because it needs more precision in this case. Normally the scaling history is 1024, but that kind of depends on the network. However, most of the networks are fine. If you are wondering about the initialization, we can just do simple as putting it 1 and it kind of trains and then gets history. So most networks are robust, so it's not like it overflows or underflows from the very beginning. Now, if you are training asynchronously with multiple GPUs, you can or just ignore syncing the scaling history because, well, it depends. There is a trade-off there. I'm not going to details. In general, the framework should take care of it. Now, this is kind of in practice. This is not an MLPerf number, but this is our recent values from NeMo, which is our framework for LLM training. So, for example, for Llama 7B, we can observe almost 4x speedup. However, I want to stress that this is from A100 to H200. So we also change the generation. Plus, we change FP16 to FP8. But this is a real speedup that you can get going from A100 to Hopper architecture. So in this case, if your model trained, I don't know, if you are model training in 2 days, you can go to Hopper and maybe you can get Llama 7B and train in 2 days as well. Maybe it will help, maybe it will not. But yeah, FP8 gives more around 3 to 4x speedups in normal cases. Even on Hopper, on H100, you don't have to go to H200 for that case. Okay, the second optimization, and it starts to be funky now. LLMs are large. I mean, GPT-3 is pretty big network. The whole checkpoint takes 3.2 terabytes to store, and you need to copy those weights and put them on devices. So we need 32 GPUs to make it actually run. And then you have to decide how do you want to split your model. So first of all, it runs. Second of all, it's fast and efficient. So we kind of end up with 3 kinds of parallelization. First one is TP, tensor parallelization. Second one is PP, pipeline parallelization. And of course, data parallelization at the end. So yeah, let me walk you through the diagram. So this is kind of a smaller node. Normally we have 8 GPUs, but for the purpose of this presentation, let's say we have 4. So TP group usually is stored within the GPU. We do that because GPUs inside a node are connected with NVLink, and NVLink is very fast, very low latency and high bandwidth. And there is a lot of communication going through TP, so we want to make sure we can take advantage of the NVLink speed. On the other hand, if you go to PP, to Python parallelization, you need to transfer a lot of data, but not that often. However, you still want to take advantage of our cluster topology. At NVIDIA clusters, we built the fabric in a full fat tree scheme. What it means is you have 3 levels of switches. The leaf switch, which connects around 20 nodes. We have core switch, which connects around 7 leaves, meaning 140 nodes, and you have spine switch that connects all the quads, so all the bunches of 140 nodes. So if you want to go fast, you need to make sure how the connectivity works. In our case, we have rail optimized communication, meaning GPU at node 0 is connected through only one switch to GPU 0 on node 1. So we want to go that, so we want to make the pipeline parallelism go around rails, meaning from GPU 0 to GPU 0 on the situation. So first of all, we can work the TP through NVLink. So we kind of can process the model in parallel very fast through NVLink, and then we shift the whole activation to another pipeline group through rail optimized communication. On top of that, but this is too confusing to actually draw, you have data parallelization, which kind of connects all the groups together. Now, the last optimization I would like to talk about is pipelining. So the model in general is too large to train with a batch size of multiple instances. So normally what we do, we train with batch size of 1, and that's because we really cannot afford additional memory. In the naive situation, as here, you can see that mini batch size has size 8. Those are the blue squares, and for the purpose of the presentation, we have 4 devices. So if we took the naive approach, we need to store the activation from all the samples in the mini batch size, and that's normally blowing up the GPU memory. You can add more GPUs, of course, but that's again inefficient. So what you can do is, okay, coming back, the gray squares, rectangles are something which you call pipeline bubble, meaning if you are running one image at a time, you will end up with idle GPU, and this is waste of efficiency. And we are trying to do something smarter to decrease, first of all, the memory usage and the pipeline bubbles so we can train efficiently. So what we did is we introduced interleaf pipeline, meaning we can just start processing a single sample from a mini batch. And when we are done with the first one, we can start backpropping it right away. We don't wait for the whole batch to finish to start backprop. We can do that as soon as the first sample, which we call micro batch size, is processed. In this situation, we have to store only the first 4 activations and first 4 samples in the mini batch, and then we can get a lot of memory optimizations. If you kind of count the pipeline bubbles, the situation is the same. So we are not getting any faster by doing that, but now we can get much more memory from our GPUs. Now the last trick is you can interleave the pipeline, meaning what you can do, instead of slicing the model only and giving just one piece of the model to a GPU, you can give 2 pieces, but from a different depth of the network. And then when your pipeline parallelism pushes the layers up, you can just come back to the same GPU. So if the GPU had a bubble, was inside the bubble and was not doing anything, suddenly you can throw additional chunk of the data at it and then keep it busy. So in this case, you have interleaf pipeline of size 2, meaning you split the model on the same GPUs in the two separate chunks. So they have dark blue and light blue. And when you if you finished processing the first batch, you can come back to the same GPU and feel part of the pipeline bubble. And this situation, not only you are saving memory, but also getting a lot of perf out of the idle time of GPUs. Okay, wrapping up. Some takeaways. So first of all, LLMs are really fun to train. There is a lot of ways how you can accelerate that, and every % matters because people are training LLMs for months at huge data centers. So every % can be easily converted into dollars, and that's the best you can have, right? You can really describe your optimizations in terms of dollars. If you are training LLMs in FP32, please don't do that. That's just wrong, and it works perfectly well in BF16, and now it works perfectly well in FP8 as well. If you are running Hopper, you will get some perf out of it as well. So if you have access to H100, and probably you should because it's everywhere in the cloud right now, I really recommend going to FP8 because it saves a lot of money because you can get scaling up to 4x going from I100. And then MLPerf has a release every 6 months, more or less, and I really recommend just throwing a glance at the results because that shows how the AI training hardware landscape changes. We are there always, so maybe we'll get some glance at new NVIDIA results. I also put some information about the additional materials. So of course the MLPerf and ML Commons page and Transformer Engine, which is our, let's say, internal framework for FP8 routines. You can really take the blocks. It's integrated very well with PyTorch. We are integrated with JAX. So you can just take layers and plug them into your model right away. On top of that, we have NeMo that integrates already Transformer Engine, which is kind of high-level framework to what we use to train LLMs. We do that internally at NVIDIA, but that's available for everyone, and we really recommend looking into NeMo. And last but not least, there is GTC coming. This is our, let's say, big yearly conference. The virtual attendance is free. There will be a lot of very interesting talks about LLM. I really recommend because there's a lot of really cool information shared there. So everyone is welcome. Thanks a lot.
Thank you. Okay. We have a delay anyway, so if there are no questions, we can just go to the after party, and maybe there were some questions then during the networking part. Thank you, Michal, once again. Thanks.